Okay, so we're going to look at some examples now for hypothesis testing. But first, let's review the steps for hypothesis testing. So if you're going to test using p-values, and keep in mind p-values are now pretty much the most common way of doing a hypothesis test. Very rarely do we use critical regions anymore. I will say when it comes to practicality, p-values are going to be the most useful for a z-test statistic, and critical regions are going to be the most useful for a t-test statistic. But it's important to know how to do both, because if you're doing some actual use statistics, then chances are you might run across both in literature. So using p-values, the first step is to state the null hypothesis and the alternative hypothesis and alpha. This first step, in fact, the first three steps essentially are the same regardless of which method you're using. So first thing, state the null, state the alternative, and state alpha. Second step, figure out which type of test you're going to use. So whenever I say the type of test, it's either going to be left-tailed, right-tailed, or two-tailed. Next, you want to determine the test statistic you're going to use. So the test statistic is either going to be z or t for our purposes because we're only looking at means. And you want to calculate that test statistic. So remember, the formula is always going to be very similar. So for a z-test statistic, so zx bar is going to equal to x bar minus mu over sigma over square root of n. So remember, we use z whenever we know sigma. And if it's a t-test statistic, tx bar is going to equal to x bar minus mu over s over square root of n. So remember, we use a t-test statistic whenever sigma is unknown. But other than that, the formulas are the exact same. So now, those three steps are the same regardless for which method, p-values or critical regions. Now's where we start getting the differentiation. So for p-values, you want to find your, if you have a z-test statistic, go to your standard normal table. And then find your area. So if it's a left tail, just look up your z-test statistic. There's your p-value. If it's a right tail, 1 minus the value off the table for the z-test statistic. And if it's two-tailed, look it up, do 1 minus it, and multiply it by 2. For a t-test statistic, you're going to end up with an interval here because the fact that we're using a table. If you use some technology, whether it be JMP or your TI calculator, it'll give you an exact test statistic. But for our purposes, an interval is going to be perfectly fine. So to find the interval, you start at the degree of freedom, n minus 1. You're going to go across that row, find your interval surrounding your t-value. In the extremely rare case your t-value is on the table, use the exact value. In that case, you would end up with just a p-value instead of a p-interval. So in this case, we're going to find the two values that surround our t-value. Just like we did when we're doing inverse normal distribution, we found the two values surrounding our probability we had. So find the two values that surround our p-value on the degree of freedom row, and then go up to the top for one-tail area or two-tail area, and those values are going to be your p-interval. Remember to always write them in numerical order, so you may have to reverse the order of the columns on the paper. Next, get your region to show the p-value or the p-interval and your corresponding test statistic, and then conclude the test. So remember, with p-values, we reject the null if p is less than or equal to alpha. We do not reject the null if p is greater than alpha. And the last step is taking it back to the context of the problem. So putting it in words, what is it saying? If you're doing critical regions, first three steps are the same. So find the null, find the alternative, find alpha, figure out which type of test, the test statistic, calculate your test statistic, and then find your critical value corresponding to alpha. So if it's left or right tailed, you're going to end up with two critical values if it's alpha over 2. But it's easy, it'll always be plus or minus the same number. So remember, to find this, you can use that table 10.1 in your textbook, or you can also use the critical values of z table that we used whenever we were doing confidence intervals, although it's a little bit more complicated if you use that table. I will provide you with that table on the final exam. So I'm going to show you how to do it using that table today. And then lastly, so then sketch your region. So sketch the tails. Use the t-table to get the critical values if it's a t-statistic. Sketch your tails. The tails are going to be the rejection region. Everything else is the do not reject region. And then conclude the test by comparing your test statistic that you calculated in step 3 with that critical value or critical values that you found, and reject the null if it lies inside that rejection region. A sketch is always going to be really useful in this situation to compare. And then lastly, same thing, interpret your results in the context of the problem. So let's actually work through some examples. And these two examples, you're going to notice they're worded in terms of steps the exact same way. This is the exact same step notation I'm going to give you on the final exam. So there's not going to be any tricks. It's going to be in this exact same notation. So you don't need to memorize the steps in order. You just need to be able to know how to do the steps. I'll provide you with the order to help you do the steps. So let's look at this first example. So sunspots have been observed for many centuries. Records of sunspots from ancient Persian and Chinese astronomers go back thousands of years. Some archaeologists think sunspot activity may somehow be related to prolonged periods of drought in the southwestern U.S. So we're going to let X be a random variable representing the average number of sunspots observed in a 4-week period. So a random sample of 40 such sunspots from Spanish colonial times had a sample mean X bar is approximately 47. Previous studies of sunspot activity during this time period indicated sigma is equal to 35. So it's thought that for thousands of years, the mean number of sunspots per 4-week period was about mu equaling 41. So sunspot activity above this level may or may not be linked to gradual climate change. So does the data indicate that the mean sunspot activity during the Spanish colonial period was higher than 41? Use a 5% level of significance to test the claim. All right, so first step, we need to state our null hypothesis, alternative hypothesis, and alpha. This is always easy to figure out as long as you know what the claim is. So our null hypothesis and alternative hypothesis, usually what I look for is what is the data, what are you being asked to find? So in this case, does the data indicate that the mean sunspot activity during the Spanish colonial period was higher than 41? So higher than 41, that tells us mu is greater than 41 is the claim that we're trying to test. We're trying to test the claim mu is greater than 41. So because this has the inequality, so no equals in there, this is going to be our alternative hypothesis. So mu is greater than 41 is the claim we're trying to test. So our null automatically then, because we have mu is greater than 41 for the alternative, the null is always the other missing hypothesis. Once you figured out your claim, is always going to be the complement. So the complement of mu is greater than 41 is going to be mu is less than or equal to 41 is our null hypothesis. Alpha is given to us. It's our level of significance. So 5% level of significance. So alpha is equal to 5% or 0.05, since we always write it as a decimal. Next question we're being asked to find is the type of test we're going to conduct. So remember, type of test, this is always going to be one-tailed or two-tailed. So left-tailed, right-tailed, or two-tailed. In this case, so to figure that out, remember, always look at your alternative hypothesis. So in this case, our alternative hypothesis, mu is greater than 41. So because it's greater than 41, that arrow is pointing to the right. So this is going to be a right-tailed test. Next, we need to figure out, okay, what sample statistic are we going to calculate, and then actually calculate it. So in this case, well, let's figure out what information we have. So remember, it's determined based off of whether we know sigma or not. If you know sigma, very strong chance, and for the purposes of our class, if you know sigma, automatically you can assume you're going to use z. But just to check, it also has to meet the requirements of the central limit theorem. So in this case, we had a random sample of 40. So n is equal to 40. Remember requirements for central limit theorem, mu is greater than or equal to 30, or sorry, n is greater than or equal to 30, or the distribution is normally distributed. And so 40 is greater than 30, so we can use our z statistic. So we're going to use z because sigma is known, and because n is greater than or equal to 30. So now we actually calculate it. So z is equal to x bar minus mu over sigma over square root of n. So our x bar value we have, x bar 47. Mu is always going to be the value from your null and alternative hypothesis. So in this case, 41. Sigma we said was 35 over square root of 40. And so we do that calculation and we end up with our z equal to 1.08. Now we need to find the p-value, or the interval containing this p-value. So in this case, it's a right-tailed test, so we look up 1.08 on our table B, which is the normal distribution table. And so you get, when you look that up, you end up with 0.8599, but since this is a right-tailed test, it's going to be 1 minus that, so area to the right, so 1 minus 0.8599. Which then gives us our p-value of 0.1401. So to conclude this test, basically we want to know, do we reject the null or do we fail to reject the null, and why? So in this case, to do this with p-values, you always just compare the p-value to alpha, right? So in this case, 0.1401 is greater than 0.05, which was our alpha level. So in this case, because p is greater than alpha, large p-values, you do not reject the null. So our conclusion is we do not reject the null since p is greater than alpha. And lastly, we want to interpret this conclusion in context. So basically what this is asking you to do is to put this conclusion, so our conclusion that we rejected the null, did not reject the null, we want to put that into the context of the problem. So what is that actually saying in layman's terms, basically? So to interpret the conclusion in this context, so the context of this problem, we were asked to find, basically this is the part where you answer what you're asked. Or in other words, you're answering the claim. So in this case, our question we were asked was, does the data indicate that the mean sunspot activity during the colonial period was higher than 41? So since we did not reject the null hypothesis, null said mu is less than or equal to 41. We do not have enough evidence to say that the sunspot activity during the Spanish colonial period was higher than 41. And in this case, you also want to state your level. So we don't have enough evidence to say this at the 5% significance level. So depending on what alpha is, there might have been enough evidence. If alpha was 0.2 in this case, you would have had enough evidence to go the other way. So it's important to specify your level of significance. So you always want to say that also. So your sentence is really, it's going to be a standard sentence. It's always going to be, we either do or do not have enough evidence to say the mean blank, whatever you're testing, was blank, whatever the claim was asking, at the blank significance level. It's always going to follow that generic format. And that's all there is to hypothesis testing with p-values. So for critical regions, well, the first 3 steps are the same, right? So we find our null hypothesis, which we've already done up here. Find the alternative hypothesis, find alpha. You figure out, you're still going to do a right-tailed test. You're still going to use the exact same test statistic. So now the different part, so finding the critical regions. So remember to find the critical regions. You can use table 10.1, which is what I referred to in the notes. So to use table 10.1, you just go down, alpha is going to be 0.505. And then we're doing a one-tailed test, so 1.645 is our critical value. Now, I'm going to give you the critical values of z table that you have above that we used for confidence intervals on the final exam. So to use that table, well, you still go to your alpha value. So in this case, the table, though, is going to give you z alpha over 2. So it's going to give you the two-tailed area, basically, or the two-tailed critical value. So if we want the one-tailed critical value, so if you want a two-tailed critical value, you're fine. You just use the table. You would find the 0.05, and there's your plus or minus 1.96, which matches what you have down here in the two-tailed test. But in this case, however, we want the one-tailed test. So since this is z alpha over 2, we just want to multiply our critical value, our alpha level, by 2 to get it. So in this case, if we're doing a 0.05 level test, then we need to go to 0.10, which then gives us 1.645 for our critical value. So our critical value, ZC, is 1.645. If you're doing a right-tailed test, it's going to be positive. A left-tailed test, negative. Two-tailed test is going to be both positive and negative. All right, so let's conclude the test. So to do this, I typically recommend sketching. So sketch out your normal distribution or t-distribution. Draw your critical value. So ZC, we said, is 1.645. So everything, in this case, to the right tail, so everything to the right of this is going to be our rejection region. Everything to the left of this is our do not reject region. So then to know our result, well, we just take that statistic we calculated before, so 1.08, and draw that wherever it goes numerically. So z equals 1.08 is here, roughly here. And in this case, it lies in our do not reject region, so we do not reject the null. Because our z value does not lie in the rejection region. And that's all there is to it. All right, let's look at another example. So the drug 6-MP is used to treat leukemia. So remission times in weeks for a random sample of 21 patients using 6-MP was found to have a mean time of 17.1 weeks and a standard deviation of 10 weeks. So we're going to let X represent the remission time for all patients using 6-MP. We're going to assume X is mound-shaped and symmetric. So a previously used drug had mean remission time of mu equaling 12.5 weeks. So does the data indicate that the mean remission time using 6-MP is different either way from 12.5 weeks, using alpha equaling 0.01. So in this case, well, start out the same way. So we want to figure out, state the null, state the alternative, and alpha. So our null and alternative, remember, are based off of the information you have. So in this case, well, what are we being asked to test? So does that data indicate that the mean remission time is different either way? So different just means not equal to. So that's going to be our alternative, again, because it has inequality. So mu is not equal to 12.5. So our null is going to be the complement. So mu simply equals 12.5. And alpha is 0.01. It was given to us in this case. You will always be given alpha. I don't expect you to have to guess it, but you still got to state it. Type of test. So in this case, we're doing not equals to, so it's pointing both ways. So it's going to be a two-tailed test. The statistic, in this case, all we have data from a sample. So sample had a standard deviation. So remember, sample standard deviation is S. So S equals 10. So because we have S And then again, verifying criteria, X is mound-shaped symmetric, so population is normally distributed. So we can use the central limit theorem applies. So then in this case, we're going to use a t-statistic. So we're going to use t because sigma is unknown. So we have S. And X is normal, or approximately normal. All right, so to calculate our t-statistic, so same formula basically, so it's just x bar minus mu over S over square root of n. So the only difference is we're using S instead of sigma. So x bar 17.1 minus our mean 12.5 divided by 10 over the square root of 21. We do the calculations, we get 2.11 for our t-statistic. So now we need to find this p-value, or in this case, because it's a t-statistic, it's more likely we're going to have an interval for the t-value. So to do this, you go down to your degree of freedom. So remember, degrees of freedom is always n minus 1. So in our case, n was 21, so we're going to go down to degree of freedom 20. And so we want to find the values on either side of our t-statistic. So t in this case was 2.11. So we want to find the two values that surround 2.11. So in this case, 2.086, 2.528. So the two values surrounding your t-statistic on the row for your degree of freedom. And then basically just follow those two columns back up to the top. And if it's a one-tailed test, left tail or right tail, you use the one-tail row. But in this case, we're doing a two-tailed test. So there's our p-interval. So our p-interval in this case is 0.02 is less than p is less than 0.05. So always writing this in numerical order. So the conclusion, it's still the exact same process. Even though we have an interval, we think about, okay, the entire interval in relationship to our alpha. So here's 0.02, here's 0.05. Our alpha level is 0.01. So because the entire interval is up here, and our p-value is somewhere inside this interval, we can say without a doubt p is greater than alpha. So because p is greater than alpha, equaling 0.01, then, so large p, again, we fail to reject. And then taking it back to words now, so interpreting in context. So there is not enough evidence at the 1% significance level to say the mean remission time is different than 12.5 weeks. So the steps are pretty much the exact same for hypothesis testing with T or Z. They're the exact same steps. The only difference is with the T interval, we're often, because we're using a table, going to end up with an interval containing the p-value. So the process, though, still is the exact same. The difference, though, if any piece of this interval was less than or equal to your alpha value, right away, you're going to reject the null, just because there's a possibility p could be less than or equal to alpha. In this case, though, it was strictly greater than alpha the whole way. So critical values are typically going to be more exact with hypothesis testing for t-statistics. Although generally you should end up with the exact same result regardless of which way you're testing. So critical values for t, Basically, you just do it backwards from how we just found the p-value. So instead, what you do is you go up here to your area, whether it be one tail or two tail, and you pick your alpha value. So in this case, alpha was 0.01. And then follow that down to your degree of freedom, find where they intersect. So our degree of freedom was 20. So then our critical value of t in this case is 2.845. And because we're doing a two-tailed test, it's going to be the positive and negative values. If it was a right-tailed test, it would just be positive. If it was a left-tailed test, it would just be negative. So then conclusion, same process we did with the z-statistic. So sketch your t-distribution, plot your critical values. So TC is 2.845 negative, and TC is 2.845 positive. And then your test statistic, in this case 2.11. So this is your rejection region here. This is your rejection region. Here's DNR. And 2.11 falls in here. So it's less than 2.845 and above the mean. And so because it lies in the do not reject region, we fail to reject. Again, so the exact same conclusion we drew with p-value. And that's all there is to hypothesis testing.